Hello, in this video, which I'm expecting to be fairly short, I'm going to give a brief introduction to quasars, what they are, why they're interesting. A lot of people have heard the name quasar, but don't necessarily know what they are. So let's start with that name then. Quasar is a shortening of quasi-stellar. So these are quasi-stellar objects, and this is meaning that they are star-like in a lot of their appearance. So quasi means apparently but not actually. So these are objects that when you observe them, first observation might suggest that they're some kind of star, but actually they're not. Now, let's go back then in the history to see how this all came together. I've already spoken in previous videos about the great debate in the 1920s. And this was when people realized for the first time that there were other galaxies outside of the Milky Way. You know, the Milky Way, our galaxy, up until then was considered to be essentially the universe. But then in the 1920s, people realized that, yeah, it's one galaxy amongst many. And since then, people have identified or predicted that there are, a couple of 100 billion galaxies in the universe. So the Milky Way isn't particularly special from that perspective, except it's the one that we live in. So that was what was going on in the 1920s. In the 1950s, so this is in the context of knowing that other galaxies exist, radio astronomy began, and people started detecting new types of objects, which in the case of quasars were compact objects, so much smaller than galaxies. That was the main thing. They were certainly smaller than that, so that fitted with the description of quasi-stellar, that they weren't galaxy sized, so they were fairly compact, emitting a lot of radio waves, and with strange spectral lines that weren't being seen in other spectra, so not your standard stellar spectra. So this is where the description of quasi-stellar came from, that they seemed sort of star-like in the fact that they were compact, but they had these weird spectra. So were they stars? Were they not? Well, quasi-stellar seemed like the way to go as a description. So that was in the 1950s. In the 1960s, this guy called Martin Schmidt, a Dutch-American astronomer, he started piecing together what was going on with this. And he put forward that these spectral lines weren't strange lines at all. They're actually familiar lines, such as hydrogen absorption lines or whatever, but with very large redshifts, which had shifted them all the way down from optical or thereabouts in the electromagnetic spectrum down to radio waves. But to have redshifts that large, that bigger Doppler shift on these lines, then we needed one or both of very high motion away from us, very high speed motion away, or extreme mass, or both. So there was something going on. We needed a completely new type of object in order to explain it, if this is actually what was going on. So very far away, and if they're that far away, then they would have to be very luminous. They'd have to be emitting some serious power in order to be picked up at that distance with that sort of redshift. So very, very luminous, or extreme mass, or both. Well, that was pointing people towards something else that was being discussed in the 1960s, black holes. Now, black holes were still theoretical in the 1960s. There was no direct observational evidence for them, but they were the new big thing in a lot of ways, and they certainly answer a lot of questions when it comes to quasars. Now, in the 1970s, people started getting observational evidence for black holes, and that has led on to the description of quasars that we have nowadays, in that they are very, very luminous active galactic nuclei, if I can say it, active galactic nuclei. So an active galactic nucleus, usually shortened down to AGN, this is the nucleus of an active galaxy. An active galaxy is a galaxy that's emitting a lot of electromagnetic radiation that isn't coming from the stars in the galaxy. It's coming from somewhere else. So, of course, we get loads of EM radiation coming from stars, but in these active galaxies, you're getting loads of EM radiation from somewhere else as well. And this is thought to be emission due to accretion of matter onto supermassive black holes in the nucleus of these galaxies. So if you've got the center of a galaxy, so let's take some kind of spiral galaxy. So this won't be a quasar, but let's just take an example. You've got a spiral galaxy, you've got the core in the middle, you've got these, the spiral arms coming out. In the nucleus, in the core, right at the center, you might have a supermassive black hole. So, huge amounts of mass there, billions of solar masses, millions to billions of solar masses, depending on how big this particular black hole is. But we're certainly looking at millions or more if we're getting into supermassive black holes. So millions of solar masses. And you'll get matter will start to accrete on this. It will form a disk of gas around the black hole in the middle. So if there's your black hole, you'll get a disk around it, sort of circling around, and this gets hot. It's moving towards the black hole. You've got this gravitational potential energy that's getting released, and the gas is heating up. It's releasing electromagnetic radiation, and this, if you've got a supermassive black hole, is an enormous energy release. You can have some of these luminosities being thousands of times greater than the luminosity of the whole of the Milky Way. So this is really, really very luminous stuff going on here in these active galactic nuclei. Now, if you've got this, so that's where we're getting a lot of our energy from, which means that we can detect these objects a long, long way away because they are so luminous. There's talk of the one that you can actually see in the night sky. If you go out into, even amateur astronomers in the back garden, if you can get down to its magnitude 12.9, so it's still pretty faint, but you can pick it out at a push. There's a active galaxy in Virgo somewhere. I forget them. They don't have very exciting names. They're all numbers and letters. They're not particularly memorable names. And it's the most distant object that you can see in your back garden. It's getting on for about 2.5 gigalight years away. So that is a very, very long way away. And it's so luminous that if you put it at 10 parsecs away, so we're talking about its absolute magnitude, if you put it 10 parsecs away, it would be as bright as the sun is in the sky during the day. So, minus 26 or less in magnitude. So ridiculous levels of brightness, particularly when you consider this is not a linear scale magnitude, this is a logarithmic scale. So to get to minus 26 or even lower, I think it's getting on for minus 27. That is seriously luminous at 10 parsecs away. But this is 2.5 gigalight years away. So, what's that going to be? Divide roughly by 3. So about, 800 megaparsecs is what we're going to have for the distance of this particular object. So having the supermassive black hole there is giving us everything we need in order to get the luminosity, the mass, the redshift that describes the spectrum of a particular quasar. So being that far away as well is saying, well, they're old, they're far away. This is all coming back to our descriptions in cosmology about the evolution of the universe, how we're looking back in time as well when we're looking at objects that are a long way away. And because all the quasars that have been detected are a long way away, suggesting that they're much more common in the early universe than they are now. I mean, maybe they've consumed the matter that was nearby. We've got this disk of matter around a supermassive black hole. Maybe the supermassive black hole, lots of them were set up in the early universe. They emit a lot of this energy, but then eventually the disk around them gets consumed by the black hole. There's then nothing to actually emit energy anymore. It's all gone into the black hole, and the black hole itself is black. That's why it's called a black hole. So maybe there are a lot of these supermassive black holes sitting around dormant, waiting to be kick-started into life again. It could be that what's kick-starting these quasars and getting them to emit all this energy is maybe in the early universe there was a lot more interaction between galaxies. You had a lot more collisions between galaxies. You know, the universe was smaller. Maybe, you know, these galaxies were closer together, and maybe that was what was happening. You know, maybe our own galaxy in the Milky Way, maybe that had an active phase in the past and now doesn't. You know, maybe there's a dead bit at the center of the galaxy now with this supermassive black hole there waiting to go if some matter comes along, but there isn't matter there to, you know, to start falling in and get hot. You know, maybe it will reignite in a few billion years when it's predicted that the Milky Way and the Andromeda galaxy will collide and, yeah, merge with each other. Yeah, it's hard to say. So there are a lot of unanswered questions about quasars, but this is what we think they are. That's the main thing that I'm trying to get across in this video, that they're very luminous, active galactic nuclei, probably powered by supermassive black holes. And these objects were much more common in the past, which is why we can see them so far away, because they were common in the past and they're very, very luminous. So they're pretty much the most distant objects that we can see in the sky because of their immense luminosity. So there you go. That's a flavour anyway of what quasars are, just so you've got some idea of what they're about. But they're pretty exotic objects, so there's still a lot to be worked out in describing them in more detail and more clarity.